next talk from Rinat Kashaev, University of Geneva, about R-matrices from exterior algebras with braided Hopf structures. Please.
Thank you very much. I'm very happy to be a speaker at this conference. So thank you, organizers, for giving me this opportunity. So my goal is to talk about a little bit the Young-Buxton equation. Namely, I'm going to talk about, first of all, I should point out that it will be constant Young-Buxton equation, no spectral parameters. And I'm going to describe some alternative ways of constructing solutions. So needless to say that the Young-Buxton equation is a very important object, both in physics and mathematics. And to have multiple perspectives on it can help us to reveal or highlight different aspects and applications of the equation. So my outline is as follows. So first I will talk about so-called rigid R-matrices. This is a simple concept, just as some extra condition on the solutions, which is important for applications in construction of knot invariants. Then I will talk about the standard approach to construction of solutions from Hopf algebras through Drinfeld construction. And then I will turn to braided Hopf algebras and describe an alternative way of approaching Young-Buxton equation. And the main part of my talk will be concentrated around the exterior algebras carrying braided Hopf structures and associated R-matrices. And I will conclude with further perspectives. So let us start with rigid R-matrices, which is an algebraic ingredient for knot invariant constructions. So let V be vector space, and R-matrix over V is an invertible matrix in the tensor square of V, which satisfies Young-Buxton equation, and I will I write it in the braid group form. So if you have R like this, then you take R prime, which is R tensor identity, which is also called R12, and R double prime is identity tensored with R, which is also called R2, 3. And then the equation is here. Now, so far there were no restrictions on the dimension of V, but if V is finite dimensional, and if we choose a basis in V, together with a dual basis in the dual vector space, then we can define what I call partial transpose of any linear map from tensor square of V to itself. So the special transpose is denoted by tilde, like here, and it is a map from V dual tensor V to V tensor V dual, and here is a explicit formula in terms of basis and dual basis elements. And more easy is to visualize this graphically. So if I think of F as a graph like this, with two legs below and two legs upwards, then the partial transpose is just turning around the left uppermost leg like this. Sorry. Left uppermost like this, and right lowermost leg like this, and the result is a partial transpose. So the R-matrix is called rigid if partial transposes of R and its inverse are invertible as linear maps. To be concrete, here is an example of an R matrix. So we have a vector space with linearly ordered basis. And let theta be Heaviside symbol taking value 0 or 1. And the value 1 if and only if the first argument is strictly greater than the second argument. And then for any non-zero scalar p, we can define a map from tensor square of v to tensor square, which is specified on the basis elements by this formula. And as a matter of fact, so this is R matrix, and it is rigid if the dimension of V is finite. But in principle, it is R matrix also in infinite dimensional vector space because the map is well defined. And now, what is the standard approach to constructing R matrices from Hopf algebra? So it is a story called Drinfeld's quantum double construction. So we start with a Hopf algebra with invertible antipode. Then there is a procedure called quantum double construction, which gives another Hopf algebra denoted D of H, which has a universal R matrix. Then we pick a finite dimensional representation of this quantum double. And then we evaluate the universal R matrix at this representation. And the outcome will be a rigid R matrix over the vector space which underlies the representation. Here is an example. We take a UQSL2 quantum group and pick as H its Borel subalgebra. More explicitly, it is as a Hopf algebra is presented by two generators, one invertible and another one just not necessarily invertible. They satisfy Q commutation relation. A is group-like, and B is primitive or skew primitive rather. Now you proceed with the second step by construction of quantum double, and then pick irreducible n-dimensional representation. Then you will get a rigid R matrix, and the rigid R matrices are suitable for constructing knot invariance. And in this case, the outcome will be what is known as an n-colored Jones polynomial. Now, let us turn to braided Hopf algebras. So braided Hopf algebras generalize the usual Hopf algebras to the context of braided monoidal categories. And when in most general setting, they are called braided Hopf objects. But in my context, they will be algebras in the sense that the underlying the braided category will be sitting inside the category of vector spaces. So here is a couple of terminologies. So braided vector space is a vector space with an R matrix over it. And then what is a braided Hopf algebra? It is a braided vector space with 5 structural maps called product, coproduct, unit, counit, antipode, which are morphisms in the braided category and satisfy the usual Hopf algebra axioms, namely associativity, unitarity, coassociativity, counitality, antipode invertibility, and else with a braided compatibility condition. So this last condition is the only condition which differs the braided nature of the Hopf algebra from the usual Hopf algebra, because the braiding interferes in this relation through this way. But of course, one should remember that the morphisms, all structural maps are supposed to be morphisms in the braided category, which means that they are also compatible in some canonical way with the braided structure, namely this tau. It is convenient to use graphical notation, and where the braiding is represented by crossing, like in knot diagrams. And all these correspond to maps from bottom part of the diagram to the upper part of the diagram. For example, the product is given by this three-valent vertex. So the two inputs and the one output. Coproduct is dual to product, so it has a one input and two outputs. Unit just zero input, one output. Co-unit one input, zero output, and antipode one input, one output. And then the whole set of properties of the braided Hopf algebra is given by this set of relations. You can recognize here the associativity, unitality, co-associativity, co-unitality, antipode invertibility, and this is the last compatibility, braided compatibility condition. Where the braiding enters in explicit way in the left-hand side, as you see. So the usual Hopf algebra, if instead of this braiding, you put just a simple crossing corresponding to a simple permutation of vector spaces. And this part of diagrams correspond to the fact that all morphisms, all structural morphisms should be morphisms of the braided category. For example, it means that the unit should pass easily through the crossing like this from two sides. Likewise for the co-unit. As well as for the antipode, and as well as for the product and the coproduct. So you see that if you are dealing with a non-trivially braided category, then you should keep in mind that the structural maps should be consistent with the braiding in the sense of all these diagrams. And now having this diagrammatic axiomatics, we can start playing games. And in particular, we can rewrite this braided compatibility condition in the way that the braiding is entirely expressed in terms of structural constants. Like this, and in the subsequent part of my talk, this relation will be useful. Another consequence is that the product braiding and antipode satisfy this relation diagrammatically or like this as a formula in terms of letters. Here is the example. It's one of the most important examples. So we take a braided vector space, which means that we have a vector space together with an R-matrix over it. And then we construct the tensor algebra. So it is already algebra, but in fact, it becomes a braided Hopf algebra if we declare all elements of degree 1 primitive. So all elements of degree 1 correspond to elements of V, where this exponent n equal to 1. And of course, we have some more complicated braiding on the entire vector space, which underlies tensor algebra. So this is why I put hat above tau. And it is induced from the input tau here, which means that the restriction of this tau hat to V coincides with V in particular. But the induction to the rest of the space should be done by respecting all these kind of relations. So in particular, for example, if you have a braiding for generating elements, then you can create the braiding for product of such elements by imposing this relation. So effectively, there is some fusion procedure is going on when you take a tensor powers of the vector space V. Okay, and then so this is the first example, and then we can, of course, as an algebra, this is a huge free algebra on, say, on a chosen basis of vector space V, but we can reduce it by quotienting by some Hopf ideal generated by primitive elements of degree 2 and bigger. And in this case, the quotient braided Hopf algebra is called Nichols algebra. The theory of Nichols algebras is a huge subject, and which myself I learned relatively recently, and I regret that I didn't learn it many years before. Because in retrospect, when you understand what is Nichols algebra is, you realize that the theory of quantum groups is just a tip of an iceberg, which is visible above the water, and the huge invisible part is hidden under the water. And this is what is Nichols algebra compared to the theory of quantum groups. Now let me now turn to R-matrices. So what we do now, we suggest an alternative construction of R-matrices starting from braided Hopf algebras and input as input. So let H be a braided Hopf algebra with invertible antipode, and the extra piece of data which we use is a choice of an automorphism of this braided Hopf algebra. Automorphism means that it is not just an invertible linear map. It should respect all structural maps, including the braiding. And what is important to remark is that in practice, the choice of the automorphism plays the role of choosing a representation in the traditional approach. So here is the example. What we do, we pick just a polynomial algebra, which is a tensor algebra of a one-dimensional vector space. But remember, on the previous slide, we started with a vector space with the R-matrix. And what is the most non-trivial R-matrix on one-dimensional vector space? Of course, it is just a multiplication by a scalar Q. So the basis element is X, so the X tensor X is sent to Q times the X tensor X as a braiding. Now, what is how we choose an automorphism? So we choose it as a diagonal action, which multiplies by scalar. I mean, multiplication by any scalar of the generator, of course, is an automorphism. But if we choose this non-zero scalar carefully, like a negative power of braiding, then it appears that the n+1 dimensional subspace of the polynomial algebra is invariant under the action of the row R-matrix defined by this formula. So this formula makes sense irrespectively what is the dimension of the underlying braided Hopf algebra. But for this specific choice of the automorphism, this R-matrix preserves a finite dimensional vector subspace of the polynomial algebra. And now if you look what kind of R-matrix you obtain just the R-matrix producing the n+1 color-Jones polynomials, which in the traditional approach comes from quantum group UQSL2. So that's my first message, is that this approach to R-matrices is more economical in the sense that you just use a polynomial algebra and just a simple one-dimensional braiding to come up with a color-Jones polynomial.
But could you write a formula as a matrix?
No, I don't remember by heart, but it is just standard color-Jones R-matrix as an outcome. You just take x power m, x power n, and go step by step with x is a primitive element, so its coproduct is x tensor x, like delta x is x tensor x, 1 plus 1 tensor x, and then you calculate delta of x squared, like square of coproduct of x, like this. But you should be careful with braiding, because in the braided world while passing one x through other x, you should use multiplicative factors like here, and in particular for the x square you will have like this, 1 plus q x tensor x plus 1 tensor x squared, and so on. Actually, for nth power of x, you will get q binomial expansion, and so on and so forth. So you just follow all these all definitions, and you will get just the R matrix on the nose. So no UQSL2, no sophisticated commutation relations, nothing like that. Just the Hopf algebra axioms and the rules of the game. Okay, now let us turn to exterior algebra. So the recent theorem with Volodya Mangazeev. So I forgot to mention in the beginning of my talk that what I am talking about, especially the part concerning the exterior algebras, is done in collaboration with Vladimir Mangazeev. And here is a important theorem, which states that if we start from the braided vector space given by our matrix tau p, which you have seen already in the very beginning of my talk, but I repeat here the definition. So we take a linearly ordered basis in V, and then on the basis elements, we define the R matrix by this formula, where theta AB is just the Heaviside theta, taking values 0 and 1, and the value 1 if and only if A is strictly greater than B. So given this input vector space, you remember that the tensor algebra becomes a braided Hopf algebra, and then the maximal quotient by ideal JV gives Nichols algebra, and the theorem states that for this particular input, the corresponding Nichols algebra is isomorphic to the exterior algebra, non-deformed exterior algebra of the vector space, so which is in particular finite dimensional if V is finite dimensional. So, and here I'm repeating, as any Nichols algebra, it is a braided Hopf algebra, which will be denoted like this, where all elements of V are primitive and braiding is induced by tau p. So how much time do I have for the rest of my talk?
5 minutes.
5 minutes, okay. So now I will be more quick and sketchy. So there is a set theoretical basis for this vector for this Hopf algebra given by subsets, finite subsets of the basis with a notation for size k subspaces. So we just we take a product in the ordered manner, and then if we extend the Heaviside to subsets just by summing over all elements. And with this Gaussian exponent as a notation for gamma k, then we have a product rule, coproduct rule, and the antipode in the algebra. And another result is that the braiding on the underlying Hopf algebra is given by the following Moy diagrammatic formula. Moy comes from Murakami, Otsuki, Yamada. This formula actually the analog of it in the context of deformed exterior algebras was derived originally by Murakami, Otsuki, Yamada themselves, and also by Kautis, Kamnitzer, Morrison. And we give a simpler proof, which is based on this relation you have seen recently. And now we can do more. We can calculate the matrix coefficients of this braiding on the exterior algebra. So if we have four sets such that G is a subset of complement of F in E, and likewise for H, and some other intersection and some other stuff, which are represented in this Venn diagram. Yeah, or Venn or Van, I don't remember. But the essential thing is that so we define certain coefficients beta, e.g., f, h, indexed by those subsets, and then we have a explicit formula for the action of the braiding on the basis elements, where coefficients are up to a sign given exactly by these coefficients. And then we turn to R matrix rho, which uses an automorphism. So let us choose the automorphism as a diagonal action given by the size of the corresponding sets. Then again, we have a Moy diagrammatic equality for this R matrix. And as well as we have also the explicit formula for the matrix coefficients, which are denoted this time by little r, indexed by the same quadruple of subsets. And here is the explicit formula for the coefficients in terms of beta coefficients, which you have seen in the previous slide. And my last slide is that if we fix dimension of V by an integer n, then the not invariant associated to this rho R matrix is conjecturally the Links-Gould invariant associated with 2 power n dimensional representation of the superquantum group like this. And this is consistent with few calculations for small values of n and the results of de Witt concerning the Links-Gould invariance. And for the direction, so it is a challenging problem to compute knot invariance, at least for some explicit knots for arbitrary n's, and see how the invariance behaves with varying n. And then the interesting next question is to turn to representation theory of the super quantum group and to see what are the colored versions of Links-Gould invariance, because recent work for capital N equal to 2 indicates that the colored versions of Links-Gould invariance are much more sensitive to geometric properties of knots. So thank you very much for your attention. I stop here.
Are there any questions? So I have a question myself. So there are a few R-matrices for a fine quantum group already know. I mean spectral parameter dependent, but you can send the spectral parameter to infinity with some twisting transformation and get constant R-matrix. Do you reproduce all of them?
No, I don't. I think yes. I think yes, generally, because any constant R matrix, if I understand correctly, can be Baxterized, and you can associate to it spectral parameter dependent R matrix, from which you can recover by taking the infinite limit of the spectral parameter. So yeah.
Every constant R matrix could be Baxterized.
Yeah. So is it a theorem?
No, I don't know. Maybe someone know. Nobody here knows.
Okay, but I believe that it is a case.
Okay. Okay, let's thank the speaker again.
Thank you.